Hello, and welcome to Subfactors. So today we'll speak about commuting squares and vertex and spin models. So there's a lot of interesting algebra here. It's basically finite dimensional algebra. Lots of matrices, Hadamard, and many others like Pauli, Weil. Very interesting stuff. So linear algebra somehow at more advanced level. So let's find this presentation first. Here we go. So commuting squares and spin and vertex models as main examples of this. Well, let's start with something different, a bit different from subfactors. So remember, the end of the game of subfactors is to understand von Neumann algebras, right? So let's go back to von Neumann algebras. So what was the theory there? The main discovery is that the main thing is that the commutative von Neumann algebras are exactly the L infinity of x, with x being measured space. And that's the basis for von Neumann's reduction theory. I mean, right, the center has L infinity of x, and then you have this fiber decomposition. Now, in general, getting beyond that, the use of abelian subalgebras, and more precisely of maximal abelian subalgebras called MASA, is a method which is very used in von Neumann algebra. Right, an abelian subalgebra reminds me of the form L infinity of x, so you can exploit that fact a bit like von Neumann did with his reduction theory. Now, the abelian algebra, of course, is better to take it maximal, so that's why we're interested in MASA, maximal abelian subalgebras. Now, so this was known in the 40s, 50s, 60s. Now, a more recent thing which was started to be studied by Poppa in the beginning of the 80s was to look at pairs of orthogonal massa. You see, if you have two orthogonal massa, orthogonal with respect to the trace, but somehow a system of coordinates there, you can get much finer results about the von Neumann algebras. So this is something very basic, pairs of orthogonal massa. Now, what are these beasts? So let's take the simplest factor, which is the matrix algebra Mn of C. And Poppa discovered, and the proof is very simple, of course, it's just some linear algebra in a few lines, is that this massa corresponds to the Hadamard matrices. So, why is this true? First of all, if you take the diagonal matrices, a massa, the basic example is the diagonal matrices, right, inside the invariant matrices. More generally, any massa must appear by conjugated by unitary, right, delta. So now, if you're trying to find two massa, one of them is certainly delta up to a unitary, and the other one is delta rotated by a matrix. Well, now if you write the orthogonality condition, that unitary matrix must have the entries of the same absolute value. That's the criteria. Now, this means exactly that it's a rescaled Hadamard matrix. An Hadamard matrix in general means that all the entries are on the unit circle and they're also pairwise orthogonal. So rescaled, that's exactly the unitary matrices which have same absolute value everywhere. So this is very interesting because once again, starting with things like going back to von Neumann everything, you led to massa and then orthogonal massa, and in the simplest case, you led to Hadamard matrices. So these matrices are very important for von Neumann algebras. Now, what are the main examples of such matrices? First of all, you have the Fourier matrix. Here it is. You have probably met this. I mean, that's the matrix in discrete Fourier analysis. It's the Fourier matrix of the cyclic group Zn, if you want. So that's the matrix in matrix form with W being the root of unity. More generally, if you take any finite abelian group, not necessarily cyclic, you just take the Fourier coupling between G and its dual, regarded as a square matrix because G is isomorphic to the dual, right? And this is Hadamard. So of course, many other examples, but somehow the idea is that these are somehow Fourier matrices of a very general type. Now, let's go back to this massa. So these are delta and delta spin by Hadamard matrix. The second discovery now of Poppa, coming in a continuation of the previous one, is that if you take these massas inside this diagram, I mean, you could see here matrices here. This is a so-called commuting square in the sense of factors here, in the sense that the expectation here on delta and here on H delta H star commute, and their product is the expectation on 2CM, is the trace. So the thing is that such squares produced by basic constructions of factors. So the problem will be now at the even more advanced level, was this a factor associated to H. So try to understand this. Now let's do first some general theory regarding this commuting square. So first of all, what I was telling you, a commuting square in the sense of factor theory is just a commuting square in the usual sense. I mean, the diagram must commute, of course, of finite dimensional algebras with traces, such that the expectation on the middle algebras commute, and their product is the expectation onto a small algebra. Now, what you can do, well, I relabel here the square A0, A1, C0, C1 because I want the basic construction. Anytime you want to construct a Jones tower, it's better to relabel things. So this is your commuting square you start with, and by basic construction you get, of course, a whole tower of commuting squares. And in the end, you get some algebras. If you close them, you get the hyperfinite factor R in both cases. So if you want here on the right, I get an inclusion of R into itself. So factor of the hyperfinite factor R, very interesting object. So any commuting square in the sense of factor theory produces a factor of R. Now the problem is how to compute the planar algebra of this. And this is given by Ocneanu compactness. So now, well, we have to go in 2 dimensions now. So it's better to relabel once again our square. Here it is, A0, 0, 0, 1, 1, 0, 1, 1. So that's our commuting square. That's what we're doing before. But let's just do it also on the vertical and more generally everywhere. Right? Basic constructions in all senses, the right and up. And now if you want to compute, actually it's better to look at this factor here, A infinity 0 included into A infinity 1. If you want to compute the Jones tower, that's exactly what you get here, A infinity 2, A infinity 3, and so on. And the commutants now, if you look, let's take K equal to, for simplifying, so the commutant of this inside of this, that's what we're calling P2, the second component of the planar algebra. Well, you don't have to, Ocneanu compactness tells you that you don't need to compute all these limits and everything. It's just enough to do the constructions here, just that, right? So this is the commutant of A10 into A02, everything taken inside A12. So it's a linear algebra problem, and it's the same for any K. So in order to compute the planar algebra of this factor here, it's enough to take the commutants of this guy to what you obtain here by basic construction. So it's a very simple, well, not very simple, but it's a linear algebra question, that's all. So what are further results now? Well, there are many, many interesting examples of factors which appear in this way. We already talked about Hadamard matrices. So these are what was the square C here, Mn here, and then 2 orthogonal massas here. These are called spin models by Jones for certain reasons. Also the vertex models where you have C and then matrix algebras everywhere. And here matrix algebra, here matrix algebra, and here the tensor product. But of course the embeddings can be spin by unitaries. So these are very interesting because they are related somehow to statistical mechanics. I mean, if you take these lattice models, with can be either vertex or spin, depending on where you put the atoms and the interactions on the edges and on the vertices, or vice versa. And you can obtain such squares. Somehow the data that you need is a unitary, and that's the matrix of Boltzmann weights. And if you do all this two-factor business like Ocneanu compactness, all that computes the partition function of the model. That's somehow the reason why these are called models. It's really statistical mechanical models, but in a bit of an abstract sense. So all these beasts are talking about Hadamard vertex spin. They have this common property that sin is in the lower left corner. So it's something like this. And this will get to them in detail later. Actually, they correspond to quantum groups and have integer index, of course. Now, in non-integer index, there are also many, many interesting examples. In fact, you can prove that, once again, Popa, that any finite depth factor appears from a commuting square. Why? Because the commuting square comes somehow from the Bratelli diagram, which starts at a certain point. That's what means finite depth. That the principal graph is finite. So out of that graph, if you want to compute such a commuting square, and since I was already telling you that the graph determines the factor, So the commuting square determines the surfactor, and actually it can be recovered the surfactor via this procedure. So very interesting. Of course, yeah, all this in the hyperfinite case. So this is very, very interesting. Now we won't get, this is very technical. I mean, there's a lot of work of Popo, Ocneanu, and many others. So we'll just focus on these vertex spin models and more generally on squares having seen the lowly of corner, just to explain a bit how these things work. So as I was telling you, yeah, that's what we want to do. And our claim is that this is a fixed point surfactor with respect to the certain compact quantum group. So let's see first how to construct this quantum group. So that's your data. So it's a diagram, but the expectations commute and the product is the expectation here. That's the surfactor condition. How to construct the compact quantum group G. The idea is very simple. You're looking for G such that the diagram is like this. I mean, here, tensor sub G is a kind of tensor product there with a G action, something involving cross products, things like that, fixed points. So the square here, of course, is C, here is A, here is D. So somehow the quantum group must solve this equation. The algebra, which was B here, let's go back. You see, this B here must be written in this form. And this can be done with standard via modeled out by a certain ideal. I mean, it's a so-called Hopf image factorization procedure. We'll be back to examples later. This is a bit abstract now. Now, once you are done with this, it's very easy to perform the basic construction. So you just get something like this. I mean, you see, and also in the other senses in the vertical. I mean, you get the complete diagram just by performing the basic constructions for the corresponding algebras here. So let's look at the upper row. So A, this was the commuting square, A tensor C and A tensor D. Now, of course, here it can only be A tensor E, with E being the basic construction for C into D, and so on. So everything, the whole horizontal tower can be obtained like this, and also the vertical one. You can get the whole thing into dimensions. These are tensor products with respect to G. The computations, well, it's exactly the same thing as for fixed point surfactors. I mean, for trying to compute these Jones towers, that's somehow how it works. So the conclusion is the following: the surfactor appears as a fixed point surfactor. If you look what happens there in the limit, it's a fixed point surfactor. The quantum group is obtained in this way, and the planar algebra, of course, by Ocneanu compactness, everything can be computed in terms of G. So that's something quite general. Now let's go back to Hadamard matrices and understand how these things really work. So my claim is that the construction is extremely, extremely simple. So given an Hadamard matrix, we don't need any surfactor of Orthogonal or MASA, just the Hadamard matrix. We associated to it this representation of C of Sn plus, the quantum permutation algebra, simply mapping the coordinates to these rank 1 projections. So I take H1, H, and the rows of H, which are pairwise orthogonal, and they're regarded inside the torus. I mean, the entries are on the circle. So that's why I can divide. And this thing, if you look at the rank 1 projections on these things, they sum up to 1 on each row and each column. I mean, that's just the Hadamard condition. So they form a so-called magic matrix, and that's what's needed for having a representation of C of Sn plus. So I make the representation, and then I'm looking at all the quantum groups for a single factorization, and I pick the smallest one. So that's the so-called Hopf image construction. And that's it. I mean, any H, Hadamard matrix, produces a quantum permutation group in this way, right? You just take this magic matrix and factorize, that's all. Now, as the theory, first of all, is that this is the quantum group we're talking about. I mean, comparing the surfactor, planar algebra, everything. So that's kind of standard. Now, as examples, we knew that Fourier matrices are the basic examples. Well, here you can only get G, right? That's what you get. So if you take the Fourier matrix as G associated to G, you're of course G itself acting on itself, right? Like a K action. Also, a very elementary is the fact that for a product of Hadamard matrices, you get a product of quantum groups. Now, the problem is how to get beyond that. And if you look at, well, the Hadamard matrices, that's a complicated business. There are a lot of things not there. And beyond the Fourier matrices, you have the deformations of the Fourier matrices. And there is a long story here. Some of the final result is the following. Given two groups, you can take this tensor product of Fourier matrices and deform it. That's the so-called Dita deformation method. And then you can compute the subfactor quantum group, everything that's work did first by Bernstein in the subfactor context, and then by me and Bichon. But finally, remember from last time, what you want to compute is the spectral measure. That's the main thing. And here it is your spectral measure. Once again, that's by me and Bichon. It's well, it's a Dirac mass here plus a free Poisson law or Marchico Pasteur. So you get free Poisson. And this holds for generic Dita deformations or for formal ones. When you take well, particularizations, it becomes very complicated. So there's some work here, more work by Bichon and by myself. So these guys are Bernstein, Vanica, Bichon, and then me and Bichon separately. So there's something still evolving here. So very interesting. Now, how to get beyond this? Of course, there are many Hadamard matrices still waiting to be studied, like the Pelly ones or Williamson, well, many interesting examples. But there's also some other direction. I mean, forgetting now about this subfactor business, all this fits into the matrix model theory for quantum groups. So there's been a lot of work here, and we have a whole theory going on. And there, the central object is not exactly Hadamard things, but rather the Pauli matrix model for S4 plus. So it's very similar to the Hadamard construction. You do somehow the same thing, but instead of the rows of Hadamard matrix, you take the Pauli matrices, the quaternions. And this is very interesting. That's something I did with Benoit Collis, and then with Bichon. It's related to many things. And then more recently with Nikita, I discovered that this has a generalization at higher order quantum computation groups given by the Weyl matrices. So well, this is quite interesting. So it's we're finally getting at least the integer index starting from these things of Jones into Weyl matrices, all that, and there's probably a relation with statistical mechanics, but this is not understood yet. Many open questions here. Okay, so see you next time. We'll talk a bit about these two. So we'll have a lecture somehow about classification problems in factors next. See you soon.